In single variable calculus, we've studied the equation of a line. In its point slope format, it would be y minus y naught is m the slope x minus x naught. The x naught, y naught sort of fixes a location where the line has to go through it, but there's many lines that go through any particular fixed point. So I also have to give you something about its sort of orientation or how it tilts in the plane, and that's what's given by the slope m. And then if I have some other point, point xy, then it needs to satisfy this particular condition. So now what we want to do in this video is generalize this to higher numbers of dimensions. So let's consider the three-dimensional case. I've got an x, y, and z axis, and I've got some line that goes through this particular space. Now, what I'm going to do to find an equation of this line is rather analogous to the lower dimensional case. First of all, I'm going to put some particular point on that line, some p naught that has coordinates x naught, y naught, and z naught. And while I'm at it, I'm going to define a vector r naught, and r naught is the vector that begins at the origin, that's its tail, and its tip is at this point p naught. This fixed point is analogous to the x naught, y naught we saw before, but what's the analogy for the slope, the m, the way that that line tilts or orients itself in now 3 dimensions? Well, instead of just a single scalar, I'm going to give you a vector. It is the vector v, and v is just some vector, some non-zero vector that lies along the line. That is, this vector v is completely parallel to the line. Now, the hope is this is going to be sufficient. Knowing this point and knowing this v, sort of analogous to the slope before, is enough to describe all the points on this line. That is, if I take some other point, let's call my generic point p, it's got coordinates x, y, z, these are completely generic, and while I'm at it, I'll call the vector that goes from the origin out to this p, I'll call that thing r. And what I want to do is find some constraints on these x, y, and z. Now, you'll notice that I'm getting close to a triangle here. I have this r naught vector, and I can add the v vector, but the tip of that is not actually at the point p. But what if I stretched out that v vector a little bit? What if instead of v, I put in tv? T is just some scalar, and the idea is I've taken the vector that is on the line, and I've stretched it out until its tip is just going to be at this point p. Well, then I really do have a triangle, and I can say that the r naught plus this tv is going to be equal to the r vector. That is, writing it in its vector format, I can say that the equation of the line in 3 dimensions is going to be that the r vector can be written as the r naught plus a scalar multiple t of that v vector. And that's my equation of a line. Now, the idea of this construction is that it works no matter where that p is, where the point x, y, z is. For instance, if I take this other p and this other r that goes out to it, well, now I can still make a triangle, but that t is going to have to be a negative value now, and probably a negative less than 1. But I can still make a triangle. By doing that, I can say that my new r is the old r naught plus this new t times v. So when I think of this, I think I've got one fixed point, this x naught, y naught, z naught. I have this sort of direction vector along the line of v. And by starting at the p naught and going out some multiple of that direction vector, I can get anywhere else on the line. To think about this sort of analogously with driving down a highway, if you say you want to go some distance down the highway, you actually have to do 2 things. First of all, you have to get on the highway, like you go from your origin to the first location on the highway. That's kind of like your p naught. And then you drive down the highway. Well, you maybe specify are you going north or are you going south, but you have your direction, your v vector, and then you do some multiple of that. Maybe you're going to go, say, 100 kilometers down this particular highway. So in that same analogy, we can say that our r is equal to an r naught plus a tv. Now, you might be thinking that these 2 different equations, the vector equation that works generally in n dimensions and the one we saw before that works in the plane, actually look pretty different. There's a t in this vector equation, for example, but not prior. So what's going on there? Well, if I imagine this vector equation applying in the 2-dimensional case, well, what would be the v vector? Now, if I chose, for instance, to step 1 to the right, well, what would happen? Because I have a slope m for my line, if I'm going to step 1 to the right, then I'm going to go up the amount m, which is to say that my v vector in 2 dimensions could be written as 1, m. So then if I use that and I take this vector equation, which in two dimensions would really be separated as two different equations, so I'd have x is equal to x naught plus t times 1, and y is equal to y naught plus t times m, then if I solve for t and plug it in, I get exactly what we had before. Y minus y naught is mx minus x naught. So indeed, these two different ways of thinking about it, they are exactly the same.